In this video, we will discuss about the principal component analysis with its basic concepts, need for it, advantages, and its uses. PCA works by transforming the original variables into a set of new, uncorrelated variables called principal components. This reduces the dimensionality of a data set, while retaining as much as possible of the variation present in the data set. As the number of features or dimensions in a dataset increases, the amount of data required to obtain a statistically significant result increases exponentially. This can lead to issues such as overfitting, increased computation time, and reduced accuracy of machine learning models. Principal component analysis (PCA) technique identifies a set of orthogonal axes, called principal components, that capture the maximum variance in the data. The principal components are linear combinations of the original variables in the dataset and are ordered in decreasing order of importance. The total variance captured by all the principal components is equal to the total variance in the original dataset. The first principal component captures the most variation in the data, but the second principal component captures the maximum variance that is orthogonal to the first principal component, and so on. PCA is a popular technique for analyzing large datasets. It can be used to visualize multidimensional data, reduce the number of dimensions in healthcare data, resize an image, analyze stock data and forecast returns in finance, find patterns in high-dimensional datasets. The disadvantages of PCA are interpretability. The principal components are not always simple to understand or describe in terms of the original features. Information loss. PCA involves choosing a subset of the most crucial features or components in order to reduce the dimensionality of the data. But if crucial features are not included in the components chosen, information loss may also result. Outliers. Because PCA is susceptible to anomalies in the data, the resulting principal components may be significantly impacted. Scaling. PCA makes the assumption that the data is scaled and centralized. The resulting principal components might not correctly depict the underlying patterns in the data if the data is not scaled properly. Computing complexity. For big datasets, it may be costly to compute the eigenvectors and eigenvalues of the covariance matrix. This may restrict PCA's ability to scale and render it useless for some uses. The following are the steps for the PCA algorithm. First, standardize the data. PCA requires standardized data, so the first step is to standardize the data to ensure that all variables have a mean of 0 and a standard deviation of 1. Second step is to calculate the covariance matrix of the standardized data. This matrix shows how each variable is related to every other variable in the dataset. In third step, eigenvectors and eigenvalues of the covariance matrix are then calculated. The eigenvectors represent the directions in which the data varies the most, while the eigenvalues represent the amount of variation along each eigenvector. Next, choose the principal components. The principal components are the eigenvectors with the highest eigenvalues. These components represent the directions in which the data varies the most and are used to transform the original data into a lower dimensional space. The final step is to transform the original data into the lower dimensional space defined by the principal components. Then you